Alright, so we're going to do problem 57. This is a diagram. So a block of mass M1, which is 3.7 kilograms on frictionless plane incline at angle that's 30 degrees, is connected by a cord over a massless frictionless pulley to a second block of mass M2, which is 2.3 kilograms. What are the magnitude of the acceleration of each block and the directions of the acceleration of the acceleration of the hanging block and the tension in the core? So you also find the acceleration. You also find the tension, and also what is the direction of this second block is moving. So whenever you do this kind of problem, when you don't know whether this block is moving down or moving upward, you can assume it. And if your assumption is after you assume, let's say, if you assume that it's moving downward, and you found that your acceleration is actually positive, it just means that the whole thing is is moving in the opposite direction. So that's just basically that. But you do have to assume it's moving at some in what direction. So let's say we assume this whole thing to move in this direction. If this is moving upward, which means that this can only go down. Okay. So now how do we do this kind of problem? These are the two block system connected by a core, and you can consider that as a system. So as just like the previous problem, they have to move at the same acceleration. Okay, and provided that the rod itself has a negligible mass. So now, first thing first, we need to draw a free body diagram. Let's define our coordinate first. Whenever you have a incline, your new x is in this direction, your new y is in this direction. So let's see how many forces acting on block 1. So block 1, you have tension. So the tension here and the tension there, they have to be the same because it's negligible, okay? The mass is negligible, so they should have the same tension. If the tension were not the same, then the rod will break. Now, what are the forces acting on this block? We have gravity. So because we're dealing with two block system, you have to specify whether it's M1 or M2. In this case, that's your M1, so you have your M1G. The subscript now becomes very important, okay? And the other thing is that you have gravity that's downward, vertically downward, and the incline is going to exert a force on the block, and that's normal force. So that's upward, that's perpendicular to the surface, so that's your N. Okay? So altogether, there are three forces acting on the block. And this is theta, so this is your theta here. As you can see, you have to resolve the vector into x and y component in order to for subsequent calculation. Now, looking at this one, M2. So your M2, let's draw a free body diagram. It has gravity, so you have M2G, and then you also have the tension, which is upward, okay, and the difference give rise to the acceleration. So now that's applied. So that's applied the horizontal component in this case. Horizontally, it's moving. Vertically, it is not. Okay. So horizontally, let's say you have tension that's rightward, but don't forget that you have gravity that has a component that's negative. Somehow, mitigates the magnitude of t. So you need to figure out how much how much is in that direction. So this, you have M1G, and then that is sine theta, and that's your negative because it's pointing downward. And this, you have your M1G, and that's cosine theta, and that's negative. So in other words, F2G, okay, has negative M1G sine theta I hat, and then negative M1G cosine theta J hat, just by looking at this diagram, okay? So now, the net force in the horizontal will be tension, that's rightward, and the gravitational force, the component, X component, is leftward, which is this one, so minus M1G sine theta. That will be your net force. So net force in the horizontal direction is equal to MA. So because we're applying to this block, so that's your M1A. okay? And so you have the tension, you have the gravitational force as component, and that has to be equal to M1A. So when you have this, let's look at this equation to see if we can solve for our acceleration. We don't know the magnitude of tension. We have the force, we have the mass of the object, and we have the angle. We have the mass. We don't know A. So you have one equation, but then you have two variables. You have two unknowns. One is tension, one is acceleration. So based on this equation, you cannot solve for either tension or acceleration. So we need additional information in order to, for subsequent calculation. So the additional information will come from the second block. Okay? Let's look at this second block. In this direction, you have the m2g that's downward, you have the tension that's upward, so you can set up equation. And because the whole thing is continuous motion, so if this is moving up, then this is moving down. So you can use m2g minus tension, right? Because m2g is down, and then that has to be equal to your m2, mass of block 2, and then times the acceleration. So once you have this, what you can see here is that in this equation, m2 is given, t is not given, a is not given. But then now you have two equations, two unknowns, so you can manipulate the equation in order to solve for one variable. You have the t here, you have the negative t there, so we can actually manipulate this equation. Add these two equations together. How do we do that? Whatever that's on the left-hand side, you add them together and set it equal to whatever that's on the right-hand side, okay? So t and t here, they cancel each other. So what we have here is that m2g, and then minus m1g, and then times sine theta, that's equal to, when you add these two together, m1 plus m2. And you can realize that m1 plus m2 is just the total mass of the system. So now we can solve for our a, because our a now is just equal to m2g, and then minus m1g sine theta, and then over m1 plus m2. So now we are ready to plug in the numbers. So you have n2, which is, after plugging those numbers, that's straightforward. So I'm just going to give you the numerical value. And that's 0.735 meter per second squared. So that's your acceleration, okay? So once you calculate the acceleration, you'll also have to find the tension. So how do you find tension? Tension is easier to calculate. So you just plug into either one event, then you can calculate your tension. So your tension, either this equation or that equation, doesn't really matter. So you can have, I'm just going to plug into this equation. So your tension here is equal to m1g sine theta, and then plus your m1a. Okay, so everything here, you have the numerical value, so it's very easy to calculate. So you got 20.85 Newton. So this is your A value. This is your tension value. Okay? And what other thing you're asked to find? Okay, what are the magnitude of the acceleration, directions of accelerations? You can see that we calculate A here to be positive. It means that it is moving, it is in the center, the assumed direction is correct. It's moving rightward, and in this case, that's moving downward. Okay, so that is that. And now, if I ask you to calculate the normal force, how would you do that? It's not part of the problem. But if I ask you to find the n, so basically you want to sum up all the forces in the particle to see what the n value is. So you have your n here, that's upward, and you have the gravitational force that's downward. So you have your n minus m1g, and then cosine theta. The whole thing is not moving, so it's set equal to 0. So your n value is just m1g cosine theta. Okay? So you have your, I didn't calculate the value, but you have your m1, you have your g, you have the cosine 30, so you can quickly calculate that value. But this just tells you that how to calculate, how to find the normal force based on this diagram. Okay? All right. So this is, again, a very typical problem, and this is actually quite straightforward and relatively simple because you don't have to consider friction. When it comes to friction, then there's additional term, which we're going to discuss that in Chapter 6. When it comes to friction, there's additional force term that you have to consider and stuff. Okay. All right, so the next one we're going to do is 64. So 64 again is a two-block system, but it's organized a little bit different from from the problem that we just did. So let me see. All right, so this is the diagram. You have a block right here, and there's a rope connected to them, and another block there. So this is your M1, this is your M2, and that's your angle theta. And there's a force that's pushing it horizontally. Okay, so it shows that a box of mass M2, which is 1 kilogram. So this is 1 kilogram. On the frictionless plane, inclined at an angle that's 30 degrees. It is connected by a coulomb negligible mass to a box of mass M1, which is 3 kilogram. And on the horizontal frictionless surface, the pulley is frictionless and massless. What is the magnitude of horizontal force? If the magnitude of the horizontal force is 2.3 Newton, so that is given. If that horizontal force is 2.3 Newton, what is the tension in the core? And what is the largest value of that force may have without the core being slack? Again, what does that mean, being slack? When the core becoming slack, it just means that it loses tension. So tension in this case will be 0. So first of all, part A says that if this force is is given, what is that tension value? So we need to draw a free body diagram just to see what are the forces acting on both block 1 and block 2. So this one, very straightforward. There are 4 forces acting on this block. You have the M1G downward. You have the normal force, that's called the M1, and then it's only 4 forces. So you have the force that's rightward, and you also have the tension. In this case, so you have the force. The force is rightward, so I'm just going to draw it here. So force is rightward, and there's also a tension that's also rightward as well. Okay, so this is a free body diagram. You have the rightward force, you have the rightward tension. Tension is away from the contact point. So in that case, you can see that the net force in the vertical cancel each other. The rightward force, you have tension plus the force. So tension plus the force has to be equal to M1 times the acceleration. Okay? And so tension, we don't know. Force is given. Acceleration, we don't know. So again, this is a two-block system with 2 unknowns. One is tension, one is acceleration. So we need additional information from the second block. So the second block, this is on the incline. So you want to draw your reference coordinate. So you have the tension. So this indicates the block. So you have the normal force. So this is your normal force. And then you have the gravity. So this is your gravity. So M2G. And you have the tension. The tension is away from the contact point. So this is your tension. So you can see that altogether there are 3 forces acting on this block. And tension and this component from the gravity, they should cancel each other. And along the horizontal, you have the tension that is in that direction, and you have the downward M2G in that direction. So how do we resolve this? So this is the angle theta, so which means that this is your angle theta. So let's draw that. So this is a horizontal component of gravity, and that is rightward, and then you have this, that's downward. So this has M2G times opposite the angle, so that's sine theta. And then this one, you have your M2G and then cosine theta. Okay, so how do we utilize the information in order to figure out the tension? So you can see that this is rightward and the tension is leftward. So you should use this minus the tension in the so that will be the net force in the horizontal direction. So you have your M2G and then sine theta, that's rightward, and then you have the tension minus T, okay, because the T is pointing in the opposite direction. That's the only two forces in the horizontal direction, and that has to be equal to M2G, M2A, because this is F, the net force, that's equal to MA, and your M here is the block 2. So again, if you look at this two equations, you have two unknown, but then we have two equations, so you can actually solve for the unknown. And also you can see that this is, the arrangement of this is exactly like the previous problem that we had. You have the T here, you have negative T here, so we're going to manipulate these two equations, add them together. So on the left-hand side, T cancels, so you have F plus N2G sine theta, and that's equal to, on the right-hand side, you have M1 plus M2 times the acceleration. So when you plug in the equation, so your A, although we're asked to find T, but we can find out our acceleration first, and then plug into this equation to find out T. So in this case, you have your F, which is 2.3, and then plus the M2G, so your M2 is 1, and then 1 times 9.8 times sine of 30 degrees, and then over the total mass, which is 3 plus 1. So your acceleration, when you do the calculation, you should get 1.8 meter per second squared. Once you have your acceleration, then plug into this equation, then you can figure out what the tension is, because your tension will just be M1A minus F. So M1 has 3 times 1.8 minus 2.3. So your tension, you will have 3.1 Newton. So that is the force magnitude of the tension. And then on the second part, it says that if how much force you apply, that will make this tension, make the rope lose its tension. It becomes slack. If it becomes slack, which means that tension is 0. If tension is 0, then you can have you can just say that your F here, your F so your T is not. Your T no longer exists, so you still have your F that's equal to M1A. And on the second equation, your T is just get cancelled, so you have your M2 G sine theta that's equal to M2A. So in other words, you base all these two equations that you set up for the utilizing this diagram, and then for part B, because there's no tension, so tension just removed from the equation, and see what we have here. So what we have here is that once you have that, you can see that your A here, your A is just G sine theta, which is known, and then you plug into this equation. So your F is just M1 and then times G sine theta. Okay, so M1 is given, which is 3, G is 9.8 times sine of 30 degrees. So your F here now is 14.7 Newton. Okay, so it's not as difficult as you think. You just have the equation 1 for each block, and then you have to manipulate the equations in order to find the unknowns. And once you find the unknowns, then the rest just becomes very straightforward. Just plug in, find the acceleration, plug into one of the equations to find your tension. Okay. All right. So the last problem we want to do from chapter 5 is problem 77. I'm just going to erase this. All right, on 77, a worker drags a crate across a factory floor by pulling on the rope tied to the crates. The worker exerts a force of magnitude that's 450 Newton on the rope, which is an incline and an upward angle that's 38 to the horizontal, and the floor exerts a horizontal force of magnitude that's 125 Newton that opposes the motion. So let's say this is the floor, and this is the crate, and this is where the worker is pulling the crate. And the force here, capital F, is 450 Newton, and it's applied at an angle that's 38 degrees. And then there's a force that is acting in the opposite direction to oppose the motion. So let's say the force, the little f here, that's a friction, which is 125 Newton. And so you want to calculate the magnitude of the acceleration of the crate if the mass is 310 kilograms or its weight is 310 Newton. So for part A, when mass is 310 kilograms, and part B says when weight is 310 Newton. Okay, and you want to find the acceleration of the crate. So what we want to do is that place a dot and then find out how many forces acting on this block. So we know that there's a gravity. So this is mg. You have the normal force that's upward. You also have this applied force that's at this angle, and you have this frictional force. Okay, so if you draw a free body diagram, this is the full forces acting on this object. So you have the N, you have the mg, you have the frictional force, you have the outward external force. And it is moving horizontally, which means that vertically it should sum up to 0. Okay, so how do we find the net horizontal force? This is the force. So we know that horizontally you have Fx, which is F times cosine 38. So your F, in unit vector notation, should have the F cosine 38 I hat and then plus F sine 38 J hat. Okay? So in that case, the net force in the horizontal direction will be F cosine 38. That's rightward. Plus the negative force, which is pointing in the opposite direction, so it's minus 125. And the whole thing has to be equal to ma. So you can calculate it very easily. So you have 450 cosine 38 minus 125. That's equal to 310 times a. So what is your a value? Your a value is equal to 0.74 meter per second squared. So very straightforward to do this calculation. And of course, you can also find out what the n value is. So your n, the normal force, plus the F component, the y component of that force has to be balanced by gravity. So we can, let me just set the equation. You can plug in the number. So you have your n, and then plus the outward force, which is F sine 38, and the whole thing of minus the mg, and the whole thing is equal to 0 because it's not moving in the vertical direction. So we can calculate your n value here. So your n would just be mg, and then minus F sine 38. Okay? All right, so this is part A. You got acceleration when the mass is 310. What about when you're not given the mass, you're given the weight? So if you're given the weight, so your weight is 310, which means that your mass is 310 over 9.8 because weight is equal to mg. So you still have this equation. The only difference is that now the mass is, instead of 310, is 310 divided by 9.8. So you have the whole thing on the left-hand side stays the same, does not affect anything. So you have 450 cosine 38 minus 125, and that's equal to, now the mass is 310 over 9.8 times a. So your new acceleration now becomes 7.26 meter per second squared. Okay, so this is a very simple problem. It's just the important thing is that when you have multiple forces acting on the object, how do you apply Newton's second law to find the acceleration? You need to resolve the vector into the x and y components, sum out all the x component and set it equal to ma, and sum out all the y components together and set it equal to set it to 0 if it's not moving in the vertical direction. Okay, so that is that.